Good afternoon. I'm going to be lecturing today on Chapter 16, Seemingly Unrelated Regression Models. We have a couple of problems on problem set 4 that are related to this. And for the first time, we're going to be getting into multi-equation models, moving away from single equation models. And the modeling approaches that we've been covering feature the econometric or structural models, and you can see here that we're in the multi-equation realm, and that comes down here to seemingly unrelated regression models. We will also do simultaneous equation models, and recursive models are a subset of the simultaneous equation models. Now, alternatively, with time series data, you can also do multivariate time series models, which would be vector autoregression or error correction models, but these models are beyond the scope of our class. So what about seemingly unrelated regression models? The underlying structure is given on this particular slide. So let's, for the moment, pretend that we have M equations that we would want to take a look at. Each of the M equations are driven by a set of explanatory variables. They don't all have to be the same explanatory variables. They could be different. For example, Y1 could have a 1 period lag in it. Y2 could have a 1 period lag. And Y sub M could also have a 1 period lag. So you don't necessarily need the same explanatory variables in each equation. So how would we estimate this set of equations? Well, you can do one at a time, OLS, or even a correction for serial correlation. But we would call the use of OLS or GLS limited information methods. Limited information in the sense that they do not take into account the correlation among the error terms across equations. And this variance-covariance matrix can be expressed, as you see here, by the matrix sigma. If the right-hand side variables, the explanatory variables, are not the same across the M equations, and if the variance-covariance matrix sigma is a diagonal matrix, then SUR and OLS are the same. And if, in fact, you do have the same set of explanatory or right-hand side variables, even if this matrix is not a diagonal matrix, the SUR parameter estimates and the OLS parameter estimates yield the same result. As an illustration, and the pioneer for this was Arnold Zellner back in 1962 with his work that was published in the Journal of the American Statistical Association. Let's suppose, as we did in Zellner's example, have two firms, GE and Westinghouse, annual data for 20 years from 1935 to 54. M here corresponds to the firm, either General Electric or Westinghouse, and we have end-of-period capital stock and end-of-period value of outstanding shares. Now, even though these appear to be the same variable, the end-of-period capital stock for General Electric and the end-of-period capital stock for Westinghouse are different, and the same is true for end-of-period value of outstanding shares. Here's a picture of Zellner, University of Chicago. Now, in the Zellner model, it turns out that when one uses OLS, we see the OLS parameter estimates here, and what's given in parentheses happens to be the standard errors, not the p-values. So how do we get the sigma matrix? Well, we're going to get the residuals for GE equation, the residuals for the Westinghouse equation, and we convert those residuals to a 2x2 correlation matrix. And as you can see here, the error terms in the GE and Westinghouse equation are highly correlated positively to the tune of 0.81. And interestingly enough, when you take into account this additional information, we get the seemingly unrelated regression parameter estimates. And by taking into account more information, the use of seemingly unrelated regression results in lower standard errors vis-a-vis OLS. And we can use the Shore model as an extension of the material that we covered in pooling of time series and cross-sectional data. It only works with balanced data, and each cross-section or time series unit could be characterized by separate equations, and often it's the cross-sectional unit that comprises the separate equations. And it also allows the analyst to test for equality of the estimated coefficients across cross-sections and or time periods. And in your problem set 4, with the work for Boston and Hartford milk prices, you get an opportunity to use seemingly unrelated regression with the pooled time series and cross-sectional data. We also have an example in problem set 4 with catfish and shrimp. Now, we're going to use all NT observations in this process, the N observations corresponding to the cross sections, to T observations for time series. So this technique, even though it involves multiple equations, involves or improves the statistical efficiency of the parameter estimates. And once again, the standard errors of the estimated coefficients in the seemingly unrelated regression or Shore model are lower or at minimally the same in comparison to those through the use of OLS. The only visible downside of the estimation of the SUR models is the size of the number of cross sections, the number of equations in the system. But this limitation is not much of a constraint. I've estimated a seemingly unrelated regression model for 60 cities for a firm in Boston called Property and Portfolio Research, and that wasn't really much of a constraint. Importantly, the SUR technique may even allow for the case where the disturbance terms in each equation are not independent over time, but they follow some sort of autoregressive scheme, most commonly a first-order autoregressive scheme. And Parks and Commenta and Gilbert are excellent references on this, and so forth. Now, just to give you an illustration as to how to use this seemingly unrelated regression model technique, I'm going to be using SAS, but one doesn't have to be married to SAS or eViews or R or Stata to handle seemingly unrelated regressions. I'm just trying to give you a feel for this. So the SAS program, or the procedure that we would use, is a procedure called PROC-SysLin. SysLin short for System of Linear Equations. It turns out, similar to the example that we had in panel data, that there are 5 cross-sections or retailers, each with 165 weeks. So we have a balanced design. And the 5 retailers are HEB, Publix, HEB, of course, headquartered in San Antonio, Publix in Florida, Food Lion in North Carolina, Fred Meyer and Meyer in the Midwest. Now we're assuming for the moment no adjustment for serial correlation. So one way we can handle this problem is reading each of the 5 data sets corresponding to the cross sections, then merge them all by week, and once again retrieve descriptive statistics. And now we start with the PROC-SysLin procedure. And data all means we're using the merged data set, and merge means you're just putting together the data sets horizontally, and as opposed to stacking them vertically. And what we would have is an identification, a label, if you will, for each equation. And the label that I've chosen is simply the label of the name of the retailer. We put together their model specification, and we create or use with the option here, SUR, to indicate that we need a seemingly unrelated regression model. And we want all of the output to be contained in a new data set called retailer SUR. So we specify each of the 5 models here. And this output statement here means we're going to retrieve the predicted values that we get with seemingly unrelated regression. Because with the use of SUR, no goodness of fit measure is provided. But remember, we discussed this before. To get a goodness of fit measure, you would take the predicted values generated by SUR, compare them to the actual values, and then take the correlation and square that. Interestingly enough, you can also do a system test or S-test involving similar parameters across equations. Now, if you'll note, in the HEB equation, there's a price variable. In the public equation, there's a price variable. Food Lion, a price variable. Fred Meyer, a price variable. And Meyer, a price variable. And since we're using linear and logs, the estimated coefficients associated with each of the respective price explanatory variables happen to be the own price elasticity. So what I'm attempting to do here, and the syntax is going to vary from one package to another. So since many of you are not SAS users, I'm not going to bother in detail with the SAS syntax. But the bottom line is we have 5 equations, and we can compare the own price elasticities across equations to determine if they're, the same. So for example, in this statement here, I want to know, is the own price elasticity for HEB the same as the own price elasticity for Publix? HEB, Food Lion, HEB, Fred Meyer, HEB, Meyer. And when you compare these 5 expressions, or 5 retailers taken 2 at a time, the number of test statements you can have is the binomial coefficient 5 choose 2. And what that means is that we have 10 tests that we can perform. And here again is the retrieval of the correlation of the actual amount of units sold of this particular product manufactured by Kellogg's with the predicted values that you get from the use of seemingly unrelated regression. So in the output that follows, here's descriptive statistics, log units sold by retailer. Here, price, log price of that. And in doing the syslin procedure, the first thing you have to do anyway is just do OLS. And what I've highlighted here is the goodness of fit with OLS. And I'm focusing specifically on the own price coefficient because there's a host of other coefficients that we could talk about. Here's seasonality, for example, distribution, advertising, the use of display, the use of coupons, the use of discounting, those type of things. So here's the OLS coefficient. It should be negative, it's positive. Here's the second equation, better fit, and negative and significant for Publix. Third equation, Food Lion, own price elasticity here, negative 1.95, although not statistically significant. Fourth equation, good fit, 0.896, own price elasticity of negative 3.68 and significant. And finally, for the fifth equation, good fit, but once again, the own price coefficient positive, but not significant. Now, you have to use OLS or run OLS first in order to use the seemingly unrelated regression. And you don't have to do anything. That's automatically going to be done. The residuals then are obtained, and what you get then from the residuals in each of the 5 equations is a 5 by 5, and this top part of the slide represents the variance covariance matrix of those residuals, but then converted to correlation form. And as you can see highlighted here, there isn't a whole lot of correlation among the retailers. The highest would be 0.28, but because we do have a non-diagonal sigma matrix here in correlation form, that indicates there's some statistical gains to be had with the use of SUR over OLS. Now, the formula that we use to get these coefficients is much like the same formula that we used in panel data. In panel data, we didn't use the term sigma matrix, we used the omega matrix. I'm only using different matrices here just to indicate that a different technique. But the formula is actually the same. The formula would be X transpose sigma inverse X, that whole quantity inverse times X transpose sigma inverse Y. And what SAS does anyway, and this is not universal for one package to the next, it also creates a system weighted R squared measure. A lot of analysts use that. I don't see much downside, but I'd still rather see individual R squares reported for each equation. Then once the formula is used, we re-estimate again, taking into account that additional information. And what should happen when one compares the standard errors here in each equation, this one being for HEB, the standard errors should be no larger than the standard errors that you get from OLS. And once again, I'm highlighting the own price elasticity. So what I've done here in the slides is to replicate this for each of the 5 equations. Now, I haven't taken into account any potential serial correlation, but we'll talk about that momentarily. But now what I'm reporting are the tested of hypotheses regarding own price elasticities. So here I want to know, is the own price elasticity for HEB the same for Publix? Well, it isn't, because we're rejecting that null hypothesis. But we fail to reject that for HEB and Food Lion. We reject it for HEB and Fred Meyer, and we fail to reject the null hypothesis regarding the own price elasticities between HEB, Meyer, Publix, Food Lion, Publix, Fred Meyer, Publix and Meyer, Food Lion and Meyer, Food Lion and Fred Meyer and Meyer. Borderline significant here if we use a level of significance of 0.05. To get the correlation or the goodness of fit measures with the 3-stage least squares estimates. Now again, depending on the package you may use, this may automatically be done for you, but it isn't in SAS. So what I'm doing is comparing the predicted values with the actual values, looking at the correlation and then squaring that. So I do that for each equation. And then what I can do is put together a summary table. Now I'll have the summary table at the end. So to review at this point, I'm using a 5-equation model instead of a single equation model like we did with the use of panel data. The upside of doing that is we allow for the possibility that there could be differences in key estimated coefficients across equations, but if we pool the data using panel data, we only come up with a common or one estimate of the respective coefficients. So the use of syslin, or now here with proc model, allows us to determine whether or not there in fact are differences in estimated coefficients across equations. Now what I want to demonstrate is the use of proc model to do SUR analysis. And again, this may be superfluous depending on the package that you have. But in SAS, the use of proc model allows you to conduct the SURE analysis without adjustment for serial correlation, but that would be the equivalent of proc syslin. Or if you found that there was serial correlation, and we didn't cover that in detail in going through the examples, but there was the presence of an AR1 process, how can we handle that with the use of multi-equation models that are seemingly unrelated? Proc model is the answer to that question. So without adjustment for serial correlation, and this will give you the same answer that we got with syslin, but I just wanted to demonstrate that equivalence. But the use of proc model in SAS means you have to write out the model specification. So here we're literally writing out the specification. The A's here are the estimated or structural coefficients. The B's are the structural coefficients for Publix, the C's for Food Line, the D's for Fred Meyer, the E's for Meyer. And what you need to do if you're going to use proc model, and again, depending on what package you do, they have their own syntax. Here in SAS, we use the word fit, and we list the endogenous variables. The option is sure. We want to take a look at a Durbin-Watson statistic, and DW prob, the probability or p-value associated with the presence of positive or negative serial correlation. We have to identify in the proc model procedure what are the parameters, and we do that with a parm statement. And similar to what we were able to do in proc syslin, we use test commands to compare equivalence of own price elasticities across the respective retailers. So A1 is the own price elasticity for HEB, B1 the own price elasticity for Publix, C1 the own price elasticity for Food Line, D1 the own price elasticity for Fred Meyer, and E1 the own price elasticity for Meyer. Now to adjust for serial correlation, we have the same model statement that we have without adjustments, but we need, as you can see here in the highlighted box, this macro, which is listed as %AR. That's the syntax that SAS uses to bring into play adjustment for serial correlation. And the way this works is that we use %AR, paren, list the dependent variable, comma 1. This indicates that we want to put in or look at the possibility of an AR1 process in the HEB equation. And in fact, with the same syntax, the presence of an AR1 process in each of the 5 equations which comprise the system of seemingly unrelated regressions. We still have the same commands as we did before, and now we're in a position to go ahead and estimate that. Now, what I've done here first is to show the equivalence of proc model to proc syslin if there was no serial correlation, and also additional information. So for example, here's a repeat of the R-squared measure on an equation by equation basis that you get with proc model. And that way, with this procedure, you don't need to use the trick of comparing the correlation of the actual versus predicted values. That's already done for you, plus an adjusted R-squared plus the Durbin-Watson statistic. And then in what follows are the parameter estimates, but these A coefficients belong to HEB, B, Publix, and so on. But at the end of the day, note that precisely the same estimates and standard errors are obtained with proc syslin as you would with proc model. You get a little bit more information, with proc model in the way of goodness of fit statistics. And you can still do the testing. You also get some information on whether or not serial correlation is present. And again, these same tests can be performed with proc model just as they were with proc syslin. And here is the details regarding with the use of model that you don't get with the use of proc syslin. Evidence of the AR1 process in each of the equations. And in fact, what this tells you is that we have confirmed positive serial correlation in each of the equations. So there is a slight advantage of using proc model over proc syslin, and that's what I would recommend. Doing it first without serial correlation, and then once you find that there is serial correlation, go ahead then and re-estimate, building in that AR1 process. Now, we've done that, and we get a new R squared. Notice the new Durbin-Watson statistics are now hovering around 2. So that adjustment through that macro that I described, the percent AR macro, at least in SAS, that means the AR1 process taken into account, and now we no longer have the AR1 process with the use of Durbin-Watson. In case you're wondering, can the percent AR macro be used for higher order serial correlation? And the answer is yes. But in this example, we only needed an AR1 process. Now we get a new set of parameter estimates, the A's for HEB, the B's for Publix, the C's for Food Lion, the D's for Fred Meyer, the E's for Meyer. The only downside about proc model, you have to go back and remember what each of these parameters are associated with what explanatory variable, but that's really a small price to pay. And here, and highlighted on slide 63, are the AR coefficients that we get in adjusted for serial correlation. Notice HEB, that coefficient is significant. Publix, significant. Interestingly enough, in Food Lion, not significant. Significant for Fred Meyer, and depending on your level of significance, possible significant AR term in Meyer. So if that's the case, you may want to go back and re-estimate this again, and then remove that macro. Don't need an adjustment for, or at least it turned out that the adjustment for serial correlation really wasn't necessary for the Food Lion equation, but you could just keep it in the model as well, okay? And similarly, you can redo the test statistics. Notice when we do that, now we only find 2 instances out of 10 where the own price elasticities were not the same across equations. And here again, with the correction for serial correlation, we find that we don't have a problem with serial correlation once we've corrected using that percent AR macro. And what I've done here is simply do a comparison of OLS, SUR, and without adjustment for serial correlation, SUR with adjustment for serial correlation, just to give an idea of how these parameter estimates vary. Now, I've done this for each retailer, but let's focus on Publix for a moment. Here, this row dealing with the own price elasticity for log price. Notice for OLS, it's -287. For SUR, without adjusting for serial correlation, -273, but smaller standard error compared to OLS. Not by much, but smaller standard error. So compare the OLS column with the SUR column. It has to be the case that the standard errors here can be no larger than the standard errors associated with OLS. But that isn't necessarily the case when we make an adjustment for serial correlation, because we don't have precisely the same model. We've appended an adjustment for serial correlation. But that said, notice that the parameter estimate here is not the same. Now, I didn't report p-values. You can do that too, because I wanted to emphasize what happens to the standard errors when one takes into account the additional information that's generated from the variance covariance matrix of the error or disturbance terms. Do the same thing for Food Lion, Fred Meyer, and again, the important thing to keep in mind, the parameter estimates are not the same across the equations. And in this particular case, for Meyer, we started with a positive coefficient for price, which was unacceptable, but we actually were able to generate a negative sign. So sign changes can occur between the use of OLS, a limited information technique, versus SUR, which is a full information technique. Now, on top of that, and I'm going to have a dedicated set of slides dealing with demand systems, but often in economics, SURs play a key role in the sense that we're going to be looking at a set of seemingly unrelated regressions, but we want to impose additional restrictions so that the parameter estimates that we get in the way of own price and cross price and income or expenditure elasticities particularly possess the mathematical properties of homogeneity, adding up, symmetry, and perhaps negativity. So a common model, and they're going to be asked to do this on question 8 with the use of data for different yogurt brands, Dannon, Yoplait, Stonyfield, Chobani, and a private label or store brand. And one of the demand systems is called a Rotterdam model in 1965, developed by a fellow named Anton Barton out of the Rotterdam School. And the other model, a key one that's often used in econometric applications, the linear approximate almost ideal demand system, Deaton and Muehlbauer in 1980. The reason for focusing on the Rotterdam and AIDS model, these are very popular. Not the only ones, but what's going to happen is that they lead to a set of multi-equation models, but now we build in restrictions based on coefficients. So you can see here for the AIDS model, coefficient, a bunch of gamma ij's and beta I. And for homogeneity, for example, the sum of the gamma ij's have to be equal to 0. And for symmetry or Slutsky symmetry, the gamma coefficients have to obey a symmetric law. I'll provide more information later. Here's a picture of Deaton and Muehlbauer. And what I've gone on in the rest of the slides is to actually show how this could be done with the use of Proc-Syslin. We could have also used Proc model. So I've given all of that information, and this is designed to deal with various spaghetti sauces. And the spaghetti sauces that we have in question: Classico, Hunt's, Newman's Own, Ragu, Prego. And there are 5 of these, and interestingly enough, on problem set 4, where we've asked you to take a look at this with the AIDS model or Rotterdam model, there are 5 yogurt brands. In each equation, the dependent variable turns out to be the budget share associated with that, with the budget share being defined as the expenditure on Classico divided by total expenditure, but total expenditure happens to be the sum of each of the spaghetti sauces in question. And I believe I misspoke earlier. I said there were 5 spaghetti sauces. There's actually 6. The 6th one is a private label. In your yogurt example, you would have Dannon, Yoplait, Chobani, private label, and Stonyfield. So we get the budget shares, and they have to sum up to 1. And then we have to undergo a log transformation for each of these. There's an index created called the Stone's Price Index. And once we have the specification, we're in a position to use Proxyslin or model to estimate the seemingly unrelated regression models. And now we can impose restrictions. The homogeneity restriction imposes the fact that in each equation, the own price and all cross-price elasticities and expenditure elasticities have to add up to 0. And we also have the symmetry condition. Now this is for the AIDS model, and you'll get a set of similar conditions here for the Rotterdam model. Now, we can actually test homogeneity and symmetry in order to do that. But in most cases, you'll find that homogeneity or symmetry may be rejected. So either you can test restrictions and decide not to use them sort of as an unconstrained model, or to impose them and not worry about a test. Now, one important feature in these demand system models, because the expenditure shares have to sum to 1, one equation must be dropped in order to avoid the singularity of the variance-covariance matrix of the error terms. And in this example, the omitted equation is for private label spaghetti sauce. And if one wanted to test homogeneity restrictions, here's how I would do that with Proxyslin, and the same for the symmetry restrictions. Now, how do you go ahead then and do a seemingly unrelated regression model with Proxyslin? Here is the way we would go about it here on slide 85. And then we estimate the model. Notice we get various descriptive statistics. Here's the amount sold in terms of ounces, thousands of ounces, or standardized units in 15-ounce container sizes. Here's the prices per standard container on average, the most expensive being Classico, the least expensive being Hunt's, even cheaper than private label. Here is the budget shares associated with each of the 6 spaghetti sauces. Note that Ragu and Prego make up about 70% of the market, clearly the industry leaders, and it has to be the case that each of these have to add up to 1, and that's what this check was put in there. Now, to estimate the model, to use Syslin, or let's suppose we don't impose any restrictions, there's no imposition of symmetry or homogeneity, and no adjustment for serial correlation. So we just use OLS, that has to be done anyway for each of these. Then what is retrieved in correlation form, you see, is the variance-covariance matrix. Actually, this is the variance-covariance matrix, but this is the variance-covariance matrix in correlation form. And notice the residuals for Classico and Ragu are highly correlated, less so for Prego, and Prego and Ragu, as you might expect, highly correlated. So the mere fact that the diagonal matrix here, or the variance-covariance matrix in correlation form, is not a diagonal matrix, speaks to the fact that potential gains may be obtained with the use of SUR through the Proxyslin procedure. Here again, we get a system weighted R squared. And what we here now have is the Syslin procedure giving you the seemingly unrelated regression procedure. And what I've highlighted are in red here are the significant drivers in each of the 6 or 5 equations. Here's Hunt's, here is Newman's, here is Ragu, here is Prego, and now we have various tests. The first set of tests, or first set of restrictions, is due to homogeneity. The second set, symmetry, and in most cases, homogeneity is not violated. The same for symmetry. Okay, so if we just wanted to determine for the whole system, we can actually do an F-test to determine whether or not homogeneity and symmetry restrictions hold as a group, and in this case they don't. The reason they don't is that we have a violation here and a violation here. Okay, the remaining slides then compare OLS, no restrictions, with Classico with restrictions. And again, because you're posing additional information, not only through the use of multi-equation models, taking into account the variance-covariance matrix of error terms, the SUR should provide lower standard errors, but lower even more because now we're imposing the homogeneity and symmetry restriction on the AIDS model. So there's a clear difference in the reduction of the standard error. And once again, the parameter estimates could be different, and in fact, they may also change sign as well. And we do this for each of the respective estimated coefficients. So that's basically how to do that. And here's the actual set of statements that you would use to do what we have just done. But in this case, instead of using proc-syslin, we're using proc-model. And here are the model statements. Now, with the use of OLS and no restrictions, the SUR parameter estimates are the same as the OS parameter estimates because the right-hand side variables are exactly the same across equations, despite the fact that the variance-covariance matrix of the error terms is not diagonal. But that won't be the case if we impose restrictions, as we're doing here with proc model. So when we do that, we get a new set of parameter estimates, and at the end of the day, you'll get a chance, and I'll have more to say about the Rotterdam and linear approximate AIDS model in another PowerPoint deck that we'll cover. But the seeming unrelated regression models are quite popular and applied econometric techniques, particularly for modeling demand systems. And the principal advantage of using SUR is the fact that we obtain additional information concerning the variance-covariance matrix of the error terms in the respective SURE models, and the use of SURE results in lower standard errors, or at least no larger standard errors than the use of OLS. So there's virtually no downside. So if you're in a position where you're looking at different estimates of involving OLS, so for example in problem set 4 with the Boston and Hartford milk prices, you can use OLS as separate equations, but why not go ahead and take a look at SUR, because the explanatory variables are not going to be the same for Boston or Hartford, meaning the potential for a non-diagonal variance-covariance matrix of residuals and more precise estimated coefficients involving SUR. You're going to do that anyway on problem set 4. So get some practice there. And you'll also have additional practice with the use of catfish and shrimp example, and additional practice imposing restrictions either with the linear approximate AIDS model or Rotterdam model, in regard to the yogurt brands that I previously mentioned. So you're going to get plenty of experience associated with that. And my friends there will have another PowerPoint deck that I'll talk about dealing with demand analysis and the use of demand systems, because seemingly unrelated regression models lend themselves very easily to that. And in this case, you can impose homogeneity and symmetry as parameter restrictions, or you have the option of even testing to see if they hold. It's commonplace to impose the theoretical restrictions in spite of the fact that often the homogeneity and symmetry conditions are rejected. So that concludes our PowerPoint for today. And I appreciate your time, and that will do it.